welcome everyone. And thank you for joining me today on this session on using AI to solve impossibly hard logistics problems. I am going to try and present so that it's a little bit interesting for a very wide audience. I know that we have some OR experts in the audience, and I know that we have some people that are not necessarily AI practitioners. So I'm going to see if I can have a little bit for everybody. So I'll just go ahead and get right started here. My name is Robert Luciani, and I am the CTO of Foxrane, a company that works with building AI that can solve operational research problems or combinatorial optimization problems. And today I'm going to talk a little bit about what OR is, why there are some neat problems that I think AI is poised to solve well, and then some really techy sort of breakthroughs in machine learning that I think will make AI more compelling as an alternative to solving OR problems. And let's see if we can work our way through all of them, because we only have half an hour. I'll just go ahead and jump right in. Let me just introduce OR as what it is. I think it's been around, the notion of optimization, especially iterative optimization, has been around since Gauss, who invented the least squares approach to calculate the trajectory of the planets around the solar system back in a time when Newton and others were using analytic or calculus methods. But I think operations research as a discipline was at least coined by the British military during World War II, and it was an initiative whose purpose it was to make the use of operational resources more efficient. And one of the first use cases was to position cannons and other things to reduce the number of bullets required to down enemy aircraft by 80%. So, earlier I was having a discussion with a person about the difference between things that we can control and that we can't control and that we can control. And forecasting is one of those things where you just do your best, but given a set of circumstances where you are in control of what's happening, operations research algorithms is an unquestionable way to derive value. So the question of, where AI can derive value, this is probably one of those places where you really can find operating margins, new services, and that kind of thing. So let me give you an example of exactly how we discovered this. My team and I were working at a large telecom operator on sort of 5G scheduling. And there are two goals in scheduling. One is to have minimal latency, meaning the system answers as quickly as possible. And the other goal is to maximize throughput, meaning you can send as much stuff as you want. And the funny thing is that those two goals aren't always easy to achieve at the same time. And so you want to have an approach to optimizing the way you schedule the little packets across frequencies so that you maximize throughput while maintaining certain latency service levels that you might have had, signed up some agreements with perhaps enterprise customers or perhaps even consumers. So this is one application of optimization, and the one that we sort of discovered and translated across other applications. Another application of optimization and combinatorial optimization in specific is the network flow problem. And the funny thing about all these problems is that, companies discovered that they have these states where they want to find the most optimal configuration of states to perhaps, maximize profitability or minimize resource waste or something like that. And the right way to do it has been to go to mathematics departments and ask them, I know for a fact that we can model this electric grid as a graph. Do you have any way to determine which edge of the graph is the cheapest one for us to use when we want to send electricity across it or something like that? And a mathematician might say, yeah, we have this graph coloring algorithm that we've developed for a very abstract purpose, but we know its properties, it converges after this time, and so on. And so the OR expert never has to question whether or not the algorithm is good. You just accept it from the math community. And so a lot of that type of innovation doesn't really happen in the domain in which it's applied, but rather we get these really robust algorithms from mathematics and from computer science, and they're sort of disjoint in that way. The interesting thing here is that network flow, it wasn't really invented for any one use case. And then there are sort of things that spring to mind immediately when you think about network flow, such as electric grids, but really anything that can be modeled by a graph, as we'll see, is a target for combinatorial optimization. So if you are a shipping company and you have boxes or containers that you're sending around, the question is, how many empty containers should you have at one site compared to another site to minimize the latency required to send the package when demand increases or decreases and kind of thing. So, while you might think of network flow as something that applies to energy grids, it applies to anything that is graph-like. And I'll give you a very nice example of a typical problem of optimization that is oftentimes solved analytically, but when you model it as a graph, you'll see that it's essentially equivalent. So all these optimization problems are graphs, even though they don't seem like it on the surface. Another one that you might be familiar with is the problem of assigning specific people to specific tasks. And here's an example where I was speaking to a prospect trying to explain that if they wanted to reduce the queue to the X-ray machine, it was an optimization problem that they might want to consider. And the funny thing was that the doctor I was speaking to, she immediately understood that you would want to have it so that there's always one patient in line for the machine, not 10 patients, not 0 patients, but that you have to calculate the flow of patients, and that there's an optimization facet to it because there's a limited number of personnel, there's a limited number of physical resources and X-ray machines and all that kind of thing. But when I spoke to a manager that was higher up, they thought it was sort of an issue that the union needs to take care of. So I think if you're thinking in terms of where can I find the innovation to apply AI in an impactful way, a lot of times it's really born at the bottom of the organization, where people are really in touch with processes that can be modeled as graphs. Another last example of, or penultimate example of where you might recognize optimization from is the cutting stock problem. In this picture, I show some wood and why you might want to cut up wood efficiently so that there's no waste. But really, there's tons of really nice examples of this. For example, if you're cutting out fabric because you want to make a suit, you obviously don't want to waste really nice fabric. Television makers now have these factories that generate giant panes of glass. And the question is consumer demand. How do we cut up this giant pane of glass into multiple smaller TVs based on what we think consumer demand for different TV sizes is going to be? So, you're not going to make a 4-meter wide television. You're going to make 2 42-inchers, one 75-inch, and then a couple of small ones, or whatever, depending on what you think the supply and demand is going to be in the future. But that's another example of an optimization problem that can be modeled as a graph problem. Vehicle routing is very given. Although I have to say I was surprised that in telco, it's still fairly uncommon to model the network geometrically, shall we say. There are some researchers that are looking into tessellation, stochastic tessellation approaches to modeling the network. But in general, when it comes to anything from anomaly detection to predicting how long time it will take to get from one end to another, machine learning approaches are very sort of item-centric. You even see Google now is using a graph neural network to predict how long it would take for a car to get from one place to another, which I feel is a very limited way of looking at it, when graph neural networks are actually very much more powerful than that. So I'd like to give an example of something that doesn't seem like a graph problem, but can very easily be modeled as one. case in point. I obviously can't give exactly what customer this is, but in principle, this could be any customer. And so pricing is something that applies whether you're trying to decide the price of your product portfolio to customers, or maybe if you're trying to decide between your suppliers which items to buy. And the naive approach is, you start a business. Let's say your little business has a couple of hundred products. You're specialized maybe in animal food, and your objective is to price things in an intelligent way so that you have a good profit. And let's say this business makes 1 million crowns just by pricing their products. 1 million turnover per year just by pricing their products similar to the competition, but maybe they're a little bit nicer at the register, and so customers come back and things are good. And so this person has a nephew, let's say, that says, you should be a little bit more structured in how you price your objects. You could probably make a little bit of money. And the typical way to do this is to use a heuristic called Gutfeel and start lowering the price of products that drive sales. So that if you have cheap cat food in your pet store portfolio, people are going to come there because they always buy cat food. And if they know you have cheap cat food, they're going to come there. So you lower the price of cat food by 10%, but you raise the price of boutique cat toys by 20%. And you do it for a large part of the tail of objects that are not commonly bought, but that still are a large part of your total sales when taken in aggregate. And you'll find that by simply doing this crude optimization here, you're almost able to double your profits. Now, the cool way to do it, if you're a little bit computer savvy or if you're familiar with OR, is to use some kind of iterative algorithm to do this much more fine-grained and for every single product rather than doing it for large bins and that kind of thing. But in effect, you're basically using a computer to do a brute force approach to testing all of your products, adjusting them a little bit at a time until you get better and better. And the thing about the algorithms that we have is there are some that try this very exactly and some that sort of guess at which direction is intelligent. But in effect, they're really just trying every single combination until they're pretty sure that that other things aren't worth trying. But as you can see, using computers is always a good tool, and so you were able to lift your profitability from 1.6 million to 1.8. That's a significant lift for any small store owner or for any shareholder that might be interested in how well a company is doing. Now, we are in 2021. The question is, how do we scale this? It's one thing for a little corner shop to be doing this kind of optimization using Excel. But the fact is that even in a small country like Sweden, a pet store company can have tens of thousands of products in their portfolio with an enormously long tail of products that aren't commonly bought. And they may have dozens of constraints in terms of how much they can adjust the price, which ones they can adjust at the same time. They might have multiple goals. It might not only be to increase profits, but it might also be to reduce the churn of customers or something else. And then finally, there might be modern requirements as well, which is that customers want you to do price matching or maybe want you to do same-day delivery and a bunch of other things. And so the question is, given this giant scale and given the dynamics of this sort of modern scale e-commerce or any kind of vertical, what approaches to OR are there? Well, we do have super cutting edge OR algorithms to do this kind of optimization, but let me just talk about some of the theoretical facets of optimization and some myths that people might be harboring that might make it so that their approach to optimization already starts off and limits them in what they can achieve. The first thing worth understanding is that not all goals align with each other. In fact, most goals are fairly orthogonal to each other. The more goals you have, statistically speaking at least, the more likely it is that they're orthogonal to each other if you pick any two of them. And so the obvious way to minimize fuel consumption if you're a delivery company is to pick a Toyota Prius maybe or something and let that drive around forever. But obviously you're not going to deliver anything on time if you do things like that. So you obviously want to deliver on time and you want to minimize fuel consumption, but those two goals are not aligned with each other. You do have to have a priority with them. The same thing with minimizing the distance traveled. You might be able to do that very well if you're willing to put up some capital to purchase a couple of additional vehicles. But if you can't put up any additional capital, that is in opposition to that optimization goal. Same thing with minimizing cost. You can make it so that you don't spend anything on delivery, but then obviously your service levels will suffer. And finally, this is something that's actually quite difficult for some people to sort of grip, and I think only hands-on experience is something that can help you understand this. But online planning, I guess that's a tech term from the computer world, where if you have an algorithm that doesn't have perfect knowledge of what's going to happen, you try to do the best decision that you can as it happens. For instance, when you're trying to decide what machine, a virtual machine, should be deployed to in a data center, if you know ahead of time all the requests from customers that are going to come for the whole day, you can plan very well. But if you are getting requests every 10 seconds for a new deployment, or every second, or many times a second, and you don't know ahead of time what requests are going to be coming, you just have to do your best and plan. And you might not be able to have the flexibility of replanning. So those two things might be diametrically opposed to each other as well. So the first thing that needs to be done is to really set the priority of your goals, because it's not a matter of simply optimizing for all of them. But given that many of those goals might be in opposition to each other, you might have to optimize for one first and then the other. And you can have proportions of the goals, but you still need to do that prioritization. The second myth has to do with gut feel and how a lot of people really rely on it, and how a lot of people think that they can write heuristics by hand. But the fact of the matter is that humans are really bad at really understanding even simple statistics, which is why the notion of AGI is quite funny, and that machines need to get better than humans. Machines are better than humans. And let me give you a good example of where humans are catastrophically bad. That's at high dimensional thinking. If you think of a regular coin toss, it has a binomial distribution, can land heads or tails. And let's say you have an unfair coin so that it lands more on heads than tails. You flip the coin 16 times, let's say, and you ask somebody, if you look in this picture here, the top sequence is where the coin lands all heads. The middle sequence is one where it lands a little bit heads, a little bit tails. And the bottom sequence is the one that is all tails. And you ask somebody, given this knowledge, which one do you think is most typical? Most would probably answer the middle one, because if you were to sample from the distribution, the middle one, the ones that are similar to the middle ones would be the ones that you would get. But the fact of the matter is that in this particular case, where you have a coin that is more weighted towards heads, the top one is the most likely for you to get, statistically speaking, because heads has a much better chance of happening. And so even in this simplest example, there's an unintuitive answer for two dimensions. So imagine if you have more than two constraints, time windows and capacity. You think that you've got a grip on just those two, but I wouldn't be quite so sure. The next thing is divide and conquer. And the funny thing is that even experimental evidence here shows that it does work, but like in really controlled circumstances. So this is a pretty famous benchmark that has about 1,000 points in it. I think this is the 1,000-point one. And you might think, if you're going to be delivering packages to all these points, that it would be smart to sort of deliver to those points that are clustered together. And you might sort of divide the city into different parts and cluster them like this. But imagine then that you add an additional constraint like time windows, and that all those points there fall within a really tight time window, meaning one truck couldn't serve all of those points. You would have to send 8 trucks to serve those points, and then they would work together, sort of cluster by cluster. It would be very visible if you had sort of a high dimensional eyeball and you could split this into the dimensions of time and space. You would sort of see that there is a cluster of points for one truck that exists together in the high dimensional manifold, but it's not really visible when you look at it like this. And so if you think you're going to sit there and draw with a pen how to cluster your jobs by hand, or even expect a linear clustering algorithm to figure that out for you, it's going to be pretty tough. The next big myth that a lot of people misunderstand is that plans for n and n+1 elements are similar. It's not true. Plans for 100 cars and 101 cars are completely different. And this sort of manifests itself when people plan for the day or plan for the week and then sort of improvise during the day. So you'll see a truck here that has a plan to take this orange path, and then a customer says, "Can't you pick this up on the way?" And they improvise the blue path, which is essentially the worst possible algorithm, greedy algorithm. If you do this on a continual basis, you've basically compromised your optimal plan. So what's better is, for every time there is a change that you need to make, instead of simply optimizing and then being greedy about the little +1 elements, it's simply better to replan from scratch. The last big myth has to do with how good people think they are already at a given problem. So there's 2 ways to scale a combinatorial problem. The first one is to scale the number of elements in question, whether it's the number of items in your shopping cart or the number of cities you want to visit if you're a traveling salesman or anything like that. The second one is adding constraints that add to the dimensionality of this vector, of this problem. The picture above is now a fairly old, but a good example of, I'm sorry, the types of traveling salesman problems, the types of traveling salesman problems that we can solve nowadays with millions of cities. It's not a very difficult problem, but simply add 2 constraints: time windows and changing weights between the cities, and all of a sudden these algorithms get destroyed. And so the biggest problems that you can solve realistically with additional constraints drops from millions of points down to a couple of hundreds. And so again, the example below is an example of a stochastic weight TSP with time windows problem that is considered state of the art. So if you think that you're close to optimal because you're doing optimization, it can be very difficult, especially if you have many constraints to determine how truly close to optimal you actually are. So let's talk just for a moment about things that characterize approaches to solving combinatorial optimization problems. So this is going to get a little bit techie, and I'm going to circle back on practical applications. But to sort of set the stage for why deep learning can solve some of these problems well, we do need to understand what the best algorithms have in common when it comes to solving combinatorial optimization problems. One of the best approaches is dynamic programming. And most algorithms are sort of variants of dynamic programming approaches. Consider the problem, the Fibonacci sequence that you might want to solve for. This picture here is sort of a graph representation of the Fibonacci sequence, where you want to calculate the 5th element of the sequence. The 5th element is defined as the 4th element plus the 3rd element. So I actually don't remember what numbers are in the Fibonacci sequence, but I don't know. It's like 13 and 8 and 5 or something like that. In any case, one way of doing this calculation is by taking the third element, as you can see on the right, which in turn is defined as the second and first element. And then on the left part of the graph, you have the fourth one, the fourth element, which is defined as the third element and the second element. But you see that two pieces of computation there are the same. So it would be very silly for you to calculate them twice again. And this is the characteristic of dynamic programming. It's called optimal subproblems, specifically optimal overlapping subproblems, which means that if you've solved the third element one time, you don't have to solve it again many times. This sort of defines a structure of the optimization landscape. And this is just one property of the optimization landscape, the overlapping optimal subproblems topology or sort of texture, if you will. But there are many others that are not captured by dynamic programming, that are sort of left to the programmer to solve. For example, there is an issue of scale invariance, where let's say you want to do vehicle routing or the traveling salesman problem with time windows. The question is, if you're trying to determine the distance between two nodes as they relate in space and the distance between two nodes as they relate in time, when you optimize, you need to sort of scale the space dimension so that it matches the time dimension, so that when you take a couple of steps across that manifold, that you're not sort of skewing in one direction or another. How do you do that? It's up to the programmer. The second thing is dynamic programming doesn't really take into account the issue of input sparsity. Let me give you an exact example of what I mean. In a sentence, and when we think about NLP, language processing, every word in a sentence is related to every other word by virtue of all words in a language being related to each other. So king and queen are related to each other in many, many ways. And in real graphs and real problems, the relations between the nodes are much, much more sparse. It's not necessarily so that every node that you can visit is always attached to every other node. There might be islands. You can't reach one node from another node and that kind of thing. So input sparsity, right now, dynamic algorithms typically treat all graphs as equivalent and fully connected. Another thing is that combinatorial problems and graphs are permutationally invariant. The graph on the right is equivalent to the graph on the left. And the way this manifests in dynamic programming algorithms is if you have an input, much like a sorting algorithm for that matter, if you have an input that's partially sorted when you hand it to the algorithm, it might produce a fantastic result. And then you take the exact same data set and you simply shuffle it a little bit. Perhaps you even shuffle it maliciously, and you give it to the algorithm and it'll get stuck in a local minima. It's the same data set, it's the same algorithm, but you've shuffled it a little bit, just like this graph here. And all of a sudden the algorithm can't figure out what to do and gives a horrible result. It changes from iteration to iteration. That's definitely a weakness. And then finally, and this is an extension of the difficulty of sort of coming to grips with scale invariance from earlier. It's up to the programmer very much when you're writing these algorithms to define neighborhoods and sort of locales and how big the locales should be and the scale of that. And there are experts that do this for sure, but the interesting thing is it varies from domain to domain in terms of the data model that goes in. But in terms of graph traversal and combinatorial problems, it doesn't actually vary. So what we have is actually a number of sort of manifold structures on the loss landscape that are in common across all combinatorial problems. but that we're not really taking advantage of in contemporary dynamic programming algorithms. So where does deep learning play a role in this? Well, there's a new field that's really emerging now that's super exciting called geometric deep learning. I'm not going to be a shill for my company too much right now, but we have an implementation that I think is quite neat, and I'm going to talk about some of the tricks that are modern that I don't think a lot of people are doing that take advantage of the neat things that we see in geometric deep learning and reinforcement learning right now. So the first thing that might not be well known in the OR community, at least, is that graph neural networks align algorithmically with dynamic programming. So layer by layer and step by step, you have an alignment between a tree-like dynamic programming execution and the neurons in the graph algorithm, in the geometric deep neural network. And in this picture in specific, what you see is the alignment between a breadth first search step and a message being passed between two neurons in a message passing convolution graph network. So what you in essence have is an algorithm that's embodied in the manifold of the network. And the cool part here is that the network actually learns neighborhood principles and a bunch of other things that you would otherwise have to manually tune, variable constraints and that kind of thing. There are a number of other interesting problems that are introduced, but I think these are some of the big ones on the way in that you can at least worry less about when it comes to graph neural networks. What about some of the other properties, such as permutation invariance and that kind of thing? Well, there are a couple of fairly well-established layers that are being used in graph neural networks right now. The first one is a simple convolution where each node is affected by each neighbor. And there's a very cool intuition to this, which is we know that convolution filters that are learned for images are very efficient. And the funny thing is that images are just graphs, except pixels always have 8 neighbors, 3 on top, 3 below, and 2 to the side. And there's a sequence to them. They're not permutation invariant and so on. So the trick to a graph convolution compared to a regular image convolution is that it needs to be able to do the same filter even if the matrix is shuffled. But otherwise, in principle, it's exactly the same. The second one is attentional, where you have a variable that you can sort of scale the value of the neighbors by before it's applied to the node that you're on. And then the final one is message passing, where both the neighbor and the node that you're on can communicate to each other and agree on a vector that is then applied to the node. And this is really over the top, but there are some processes that might be neat to model this way. For example, chemical reactions or something else where you have this complicated property that you really want to communicate across the network. The thing is, this really doesn't capture some of the things that we want to achieve with our graph neural network that we want to use for solving combinatorial optimization problems. The thing is, consider a routing problem where you need to pick up a package that's really far away on a graph. That needs to affect your decision when you're very far in the center. And so you have these sort of scale problems where if you're just doing convolutions across neighbors that are right next to you, or perhaps even a couple of hops away, you're not really getting these large scale pictures that you really would need. And we do have approaches to solving this because this is specific to graphs, the way these layers are done, the attention mechanism, for example. But this is not the way things are solved in NLP. So if you look at a model like BERT, BERT has bidirectional positional encodings that are very specific to language. But like I said before, in language, a sentence, the words might be fully connected with each other, and they have a decided sequence. But in graphs, they don't. They're not fully connected. They're sparse, and they don't have a sequence. So what is the best equivalent to what BERT is doing, or what modern transformers are doing to getting the attention mechanisms that are very effective, but having them apply to the entire graph so that we can get this really nice intelligence that applies to entire graphs at the same time. And it seems that the way to do that is by using Laplacian eigenvectors. And the example you see below is the difference between PCA on the right and using a Laplacian eigenvector matrix to describe the points on the left. And you see that the Laplacian is able to keep the locality aspect of the two clusters on the left side much, much better, keep them separated specifically, much better than the PCA, linear PCA approach. And so by implementing Laplacian eigenvectors as positional encodings as part of the transformer layer, we can get this incredible performance compared to the old school, right? 1 year old, 2 years old, attentional approach that's conventionally used in geometric deep learning. The next big problem is scale. So it's very easy if you want to make combinatorial problems that have thousands, millions of elements in them that you might want to optimize, but with the quadratic complexity of some of these layers, that's never going to happen. Still, there's contemporary research showing that there are really cool ways to create latent embeddings of some of this stuff that you want to learn, so that you don't have to have gigantic, dense, square matrices describing everything. And one of the nice examples is the perceiver that was recently published by DeepMind that shows the query network as a cross-attention network, reducing the memory requirements from quadratic to not quite linear, but much subquadratic. And there are many other approaches to scaling your models and having them work on enormous problem sizes that are prohibitively large for traditional OR algorithms, at least. The last thing is, how do we even train our networks? And here I also think that there's a lot to be learned from the approaches that have been pioneered by some of the companies that are trying to make models that play video games. I've seen many implementations of deep learning applied where the using reinforcement learning, where the model is taught using a combination of an expert policy, such as beam search or something like that, and it seems like all of the best examples of reinforcement learning in these kinds of games have used a model-based value network. So what does that mean? Well, say AlphaMu, for example, that learned how to play Go and Atari in the same model. How is that possible? Well, what they do is they have a value network, and the value network, instead of teaching the model to decide what the next step is in an optimization process, as a Markov decision process, you make a network that predicts what the sum of rewards is over a long sequence. So in the case of AlphaMu, the value prediction is, am I going to win the game or not? Right? And in the case of Atari, the prediction is, what's my high score going to be? So instead of optimizing over the next step, you optimize to maximize the accuracy of the value prediction. And that's where I think that sort of the direction of reinforcement learning is going to be going soon. And all these examples of algorithms that are implemented as naive constructor search, Monte Carlo tree search, beam search, anything like that, they're just going to fall away. So now that we have all these really neat approaches, both to scalability, to reinforcement learning, and to understanding complex topologies and graphs. How can we apply it? Well, the first thing I would like to encourage is rethinking optimization as graph algorithms in general. I mentioned pricing before, and the fun thing about pricing is if you think of every price change as an edge in a graph, you can think of optimal pricing as a max flow graph problem. And then your model's task is to traverse the graph until it has found the path with the max flow on it. And the fun thing is that models can get pretty good at traversing graphs in the abstract. So I have a lot of people asking me, right, but do you have to retrain the model for every graph, for every pricing problem, or for every, vehicle routing problem? And the answer is no. Graphs are abstract constructs. You've done the bulk of the work by simply retranslating your problem as a graph. Now let the neural network do its job, because it understands high dimensional geometric space much better than you do. The next thing is when it comes to massive scale, what we've seen is what I've seen is a lot of companies either try to chop up multiple steps of optimizations into, in the case of routing, first optimizing the packing of the truck, then optimizing the routing, then optimizing other things. And I suppose it depends on the scale. Really, you can go overboard with this and just optimize hundreds of billions of trillions of things. And there's a reasonable limit to what you can do. But what used to take months for researchers to optimize an electric grid in terms of network flow can now be done in one swoop dynamically, which leads me to what I think is the ultimate application of AI. Because just to make it clear, in case somebody's under the wrong impression, AI doesn't solve anything with any guarantees of optimality. But that's seldom the case, that you need ultimate optimality. What we've found is that speed turns out to be a lot more important than optimality. Granted, if you have a certain level of optimality, speed is much more important. And let me give you one example of where you might want to do that. In the electric grid in particular, it's quite simple. I mean, we understand now that it's much more dynamic than it used to be. It's one thing if Vattenfall has their nuclear power plant and it's running, rock solid for 1 million years. But now with solar power and wind power, a country like Denmark has, I think it's more than half of all their electric power coming from wind. And it's super dynamic. You're going to rely on a plan that was done by a researcher a couple of years ago on how to optimize your grid? It's worth rethinking. Maybe AI is something that can help there. But I think a lot of companies can recognize that there is a very large dynamic aspect to their operations. And a very nice example of it, I gave the example before of scheduling VMs to a data center. But even in logistics and delivery, for traditional logistics, where we're seeing customers now that are expecting same-day delivery, and logistics companies are a little bit against it because the companies that they pick up items from are unable to produce the item quickly enough to do same-day delivery, but also because it's not a part of the way the service was designed to begin with. Contrast this, for example, with food delivery companies where a customer places an order and is expecting the food to be delivered. Here in Stockholm, I've heard the guarantee is, I'm not sure if it was 30 or 45 minutes, but in cities like Taiwan or like Taipei, they give guarantees of less than 15 minutes. Now, the silly thing here is what they do, these food delivery companies, is they have people hanging out at corners, because in a city like Taipei, you'll have the restaurants you'll have tons of restaurants at the bottom of these skyscrapers, and people in the skyscrapers typically order from those restaurants. So the reasoning goes, well, it makes sense to have a person dedicated to that area, just running up and down. But as we know from a slide that I showed earlier, that's just you thinking that n is equal to n plus 1. It's you thinking that you understand the heuristics. Just let the machine handle it, is what I'm saying. Why would that hurt? The second thing is, in this picture in particular, why I think we're reaching sort of the limits of what traditional OR algorithms can achieve is, this is a picture that's pretty cool from an experiment that Ford ran together with Microsoft to promote their new Azure quantum algorithms. And they optimized about 5,000 vehicles that had 30 potential routes per vehicle to reduce the congestion of those vehicles as they were making deliveries in the Seattle area in the United States. And this was still not an instantaneous computation, even with the help of these enormously sophisticated machines and algorithms. Moreover, the cost of some of these services can be substantial, with some of them costing in the hundreds of dollars per hour to make use of, with dedicated FPGAs and even more exotic hardware. You know, just when they say quantum, that already is top tier stuff. So why wouldn't we be using AI to do these sort of approximations? And the fact is that in certain domains where the stakes are super high, we're already seeing this. And the first and nicest example of it is DeepMind, that was using it to solve protein folding. Protein folding, again, is a graph algorithm where you have to figure out which sequence of folds leads to a given shape. And this past year, they performed tremendously amazing using AI and many of the methods that I described earlier that were inspired by work that they did when they were learning how to play Go and other games. So this will invariably spread to lots of other domains, and I don't know if it's going to go extremely quickly, but I guess the question that's open here is, what kind of a company are you? Are you the kind of company that is interested in leading or following? And geometric deep learning, for sure, in the research domain is going to grow tremendously. It's only 2-3 years old, really, catching some traction in the big conferences. But that's one thing I think you should be keeping your eye on. So in summary, if you have any questions on optimization, and specifically AI applied to optimization, feel free to reach out to me. And with that said, I hope you got a little crash course in geometric deep learning, optimization, operations research, and maybe how it all relates to logistics. Thank you. Let's see. Let's see if there are any questions or comments. Think about optimization problems. Often, implementing these solutions require dramatic changes to the organization that are hard to implement. New tools. Do you have any thoughts on the optimal path to optimal? Right. Here's a Gutfeel is a complicated heuristic. That's right. That's why it's so hard to get down on paper, right? I think one of the things that makes implementing it hard is partially a mathematical thing, which is that in real life, there are many more constraints than what people typically show. So, before I was talking about vehicle routing problem with distance and time. And, when it's time to implement these things, if you talk about job scheduling, for example, there's more than just the skill the person has and, what class the job is. There's usually a dozen constraints. And I think mostly companies are just worried that you're not going to take them into consideration. Perhaps due to the fact that taking them into consideration using traditional OR algorithms is prohibitively expensive. But then also because that's just the way things have been done with AI, where it very often is sort of an academic exercise where everything is left to the poor data scientist. You put it on the scientist's knees to come up with both a business justification and a working model and an approach to putting it into production while taking life cycle questions into account and security and everything like that. So I think what I have seen is that it's important to get, everybody says stakeholders is important, But to ground it to real operations, you do need to have it connected with somebody that's actually doing the work. The example I gave before of a doctor understanding much better resource optimization than a manager high up is a prime example of that. But one thing that is thankful in this case, and what you really need to connect it to, I'll give a nice example of it, is how it's valuable in monetary terms. We have a very thankful job when it comes to optimization. I mean, us practitioners, everybody listening, and myself, because optimizing operations tends to be very quantitative. You can calculate the savings or the increase in service levels. It's very easy to verify. It's the P versus NP thing, where if you present somebody with a schedule and say, "Look at this, we have time to do everything in a whole day, and before it took us many days to do it. To check out this schedule." You don't even have to do the schedule. You can see just by looking at the schedule that it's a good schedule. But sometimes you still do need to rephrase it a little bit. So it might be, for example, that you need to present it to a decision maker where, let's say, a decision maker has a goal for the quarter. No, not for the quarter, for the year or for the coming years, which is to reduce the amount of capital that is bound to items that have been sold to customers, but not necessarily delivered. And why are they not delivered? Well, because the scheduling and a number of other things, whatever factors, are such that there's a long process that could potentially be optimized. The thing is, you can't necessarily phrase it as, look, we're going to be more efficient at throughput of these items. You would expect them to sort of intuit what that means, but you do need to rephrase it. And because we can optimize this process and shorten the number of days, we're going to free up that capital that is the thing that you're being measured on right now. So, yeah, the sad news is it's always up to us as data scientists to do that work. But the good news is there's a very tight link between operations research and profits and that kind of thing. So from that perspective, we have a good a leg up on the other people that are doing chatbots and that kind of AI work. All right. If there are no further questions, again, please write something on LinkedIn or wherever you want and chat. I'd be glad to talk about AI, optimization, or any other number of nerdy topics with you. And I know some people that are pretty good at implementing this stuff as well. So looking forward to hearing from you. And thanks for stopping by. Talk to you soon.